All right, number 15, another rational functions problem. We're finding the limit as x approaches negative 1/3, and we want to do this from the left and from the right so we can evaluate the two-sided limit. So I'm going to go ahead and write my limit notation in here. We've got to squeeze it in. I think I fixed that on your paper. Limit is x approaches negative 1/3. And I need to do some serious factoring. I'm actually going to go ahead and do that way here at the bottom. So I need to factor my numerator and my denominator. So 2x squared minus 5x minus 12 is my numerator. My denominator is 3x squared minus 11x minus 4. All right, for 2x squared minus 5x minus 12, 2 times 12 is 24. Two factors of 24 that add to negative 5 are negative 8 and positive 3. If you are still doing slide divide, please, please, please take some time to learn split the middle or guess and check and get good at one of those factoring techniques. Because it's equal all the way through. Negative 5x is the same as negative 8x plus 3. Factoring out the 2x and the 3 still keeps us equivalent to the step above. All right, 3 times negative 4 is negative 12. So that's going to give me negative 12x plus 1x. And my parentheses match. All right, so my numerator and my denominator both share that x minus 4. So those are going to cancel. So my new function, my canceled function, is 2x plus 3 over 3x plus 1. All right, my removable discontinuity, let's do that before we forget about it since I did factor below there. Since my removable discontinuity is x minus 4, 4 is the x value. And if I plug into my canceled function, I'm going to get that y value for the removable discontinuity. So 2 times 4 plus 3 over 3 times 4 plus 1. So 8, 9, 10, 11, 12, 13, 11, 13. So there's my removable discontinuity. 4 is my x value, a little less than 1 is my y. Looking good so far. All right, x-intercept. Remember, if our removable discontinuity is at 4, our x-intercept is not going to be there. Our x-intercept is going to come from setting 2x plus 3 equal to 0. Our numerator equal to 0. And so that is going to make our x-intercept negative 3 over 2. You can have more than one x-intercept, just like you can have more than one horizontal or vertical asymptote. Set your numerator equal to 0. So I'm going to go ahead and plot that point. Negative 3 over 2, so it's negative 1/2, 0. Or negative 1.5, 0. All right, looking good. Y-intercept is what we get when we put zeros in for our x's. So 2 times 0 plus 3 over 3 times 0 plus 1. So my y-intercept is going to be 0, 3. 3 over 1. This is giving us a really good picture. We've got some really nice points with this one. All right, vertical asymptote. Our vertical asymptote we get from setting the denominator equal to 0. So 3x plus 1 equals 0. So our vertical asymptote, subtract 1, divide by 3, x equals negative 1/3. I'm going to do that in this light pink color. So I'm going to put it just on the other side. And I'm going to go ahead and label that since it's not right on a line there. And our horizontal asymptote we get from our relationship from the top and between the top and the bottom. Since we have the same degree on top and bottom, we're going to take the leading coefficient. And whether we go from our original function or what we get after we cancel, it's y equals 2/3. So 11/13 is more than 2/3. So this line that I'm putting through here is going to be just below . That looks awesome. So this gives us a really good picture of what's happening with this graph right around 1/3, or negative 1/3, which is what our limit was asking for. I'm still going to go ahead and do this table. And I'm going to use, just like I did with the last problem, our simplified form. And I'm just going to pick some values that are leading up to that asymptote. So I'm going to, I think, use -2 and -1. Not going to use -1/3. -1/3 is where our asymptote is. 0 we already have. At 0, our output is 3. I do think I'm going to go ahead and do 1 and 2 so I can get a good picture of what's going on there. So when I put -2 in, 2 times -2 plus 3 over 3 times -2 plus 1. So -4 plus 3 is -1. -6 plus 1 is -5. So -2, +1/5. So just on the other side of the x-axis. -1, let's see if I can squeeze it in here. Two times -1 is -2 plus 3 is 1. -3 times 1 is -3 plus 1 is -2. So at -1, my y value is -1/2. And that makes sense. It makes sense that that would be decreasing. And that gives us our nice curve, which gives us the limit from the left. Let's go ahead and call this one f of x. Limit as x approaches -1/3 from the left of f of x is -infinity. I think that you guys can tell what's going on from the right here. Sorry, my factoring kind of ran into my table ran into my factoring, I guess. But I want to fill in at least what's going on at x equals 1 and x equals 2 there so I can make a nice curve. If I put 1 in to my table, I get 5 over 4. So 5/4. So over 1, up 1 1/4. And if I put 2 in, so 4, 5, 6, 7, and 3 times 2, 6, 7 over 7. So I have the 0.21 there. And there you can see from the right, we're definitely increasing. I could definitely tell that from our y-intercept and where the removable discontinuity was, but it's nice to have those points in the middle just to round out your curve. So the limit as x approaches -1/3 from the right of f of x is positive. So that two-sided limit does not exist because our limits do not match and our limits are infinite. All right, that's number 15.